welcome to the deep dive. So today we are diving into something that I think you're really going to enjoy. I think as a philosopher, this is going to be right up your alley. We're talking about generalized quantifiers, and we've got some really fascinating stuff from the Stanford Encyclopedia of Philosophy to dig into today, and I think you're going to find it really uh, impactful, I guess, in terms of how we think about this topic.
Absolutely. This deep dive will chart the intellectual journey of generalized quantifiers from their initial grounding in formal logic to their far-reaching implications for how we understand, the meaning of everyday quantifier expressions. Words like every, some, and most, maybe even how we reason. So our mission today is to really provide you, a fellow philosopher, with a clear understanding of what generalized quantifiers are, where they came from, and why they're so significant. Really touch on areas that resonate with philosophical inquiry.
Okay, well, so I guess to start, let's look at the name itself. Generalized quantifier.
Right.
That kind of implies it's building off something we already know. We've got the standard quantifiers from logic. For all, there exists. And it seems like while historically this generalized part was really important to highlight this broadening of scope, nowadays you just hear quantifiers, especially in linguistics.
Right. So generalized initially, signaled this move beyond just the two, but as the field developed, it became clear that, these two are really just a small part of a much larger space of quantification.
Mhm.
So while that full term does persist, especially in logic, quantifier by itself often now encompasses this broader concept.
And it's really important to keep in mind that distinction between the quantifier expressions, right? Like the words and phrases we use, like every student, some books, most philosophers, that's different from the generalized quantifiers themselves, which are those underlying semantic concepts they represent.
Mhm.
It's like, like the word, its meaning, right?
Right. Exactly. The expressions are really the linguistic vehicles, whereas generalized quantifiers are those abstract kind of mathematical objects that give them meaning. So in formal languages, these quantifier expressions often act as variable binders, like irx in a formula, that ties the variable x to, range over individuals. And, similarly, we might use a symbol like QO to mean there exist infinitely many, again, binding a variable within its scope.
Right, and it's amazing when we look at natural language, just how many different expressions there are that function as quantifiers.
Hmm.
It's not just, everything and nothing, but also, three certainties, the only way, even like proper names like Socrates or more complex ones like most of the time, all but a few each other. It's really, I don't know, it emphasizes how fundamental quantification is to how we think and how we communicate.
Absolutely. And to really understand these generalized quantifiers, it's helpful to take a historical journey back to, well, the OG, Aristotle.
Oh, Aristotle, yes, of course. So much of Western thought starts there. His syllogistics were a very early attempt to formalize the logic of these, fundamental quantifier expressions.
Uh-huh.
All, no, some, not all. And, that was a real step forward in studying how they relate to each other.
Indeed. And, Aristotle's syllogistic logic explored the valid inferences between those quantified statements. For example, his analysis of syllogisms like all A or B, all B or C, therefore some A or C, that really reveals key aspects of his understanding of all. Interestingly, he seemed to operate with that assumption of existential import for all, meaning all A or B implied the existence of at least one A, which differs from some modern logical interpretations.
And he also noticed kind of this directional property with some.
Right.
So if some A or B, then if we expand B to like a bigger set C, then some A or C should still hold, right? That feels intuitively correct.
Exactly. Yeah. So that's this idea of monotone increasing in the second argument. And he also observed, a symmetry between some and no. So if some A or B, then some B or A. And similarly, no A or B implies no B or A, which contrasts all and not all, which don't have this reversibility. And of course, he famously explored these relationships through the square of opposition, which medieval logicians later elaborated on.
It's amazing how these early insights laid the groundwork, really, for centuries of logical inquiry. And it wasn't just him, right? The medieval logicians built on this, delving into these, really intricate sentences with quantifiers. It's like they were wrestling with many of the same questions that we are today.
Yeah, they were. But, the crucial insight from Aristotle for our understanding of generalized quantifiers is that he essentially treated these expressions all, some, no, and not all as representing binary relations between sets. So, if A and B denotes sets of individuals, sum just indicates that these two sets have at least one element in common. They overlap. And all signifies that one set is entirely contained within the other.
So not relationships between like the things themselves, but relationships between collections of things. That's a big abstraction.
Exactly. And it's that's really, the generalized quantifiers sum and all at work within a given, domain of discourse. It's interesting that this perspective of quantifier expressions as second order relations, it wasn't immediately taken up by his successors. They largely focused on this subject predicate structure of sentences, which, as our source notes, poses certain challenges when trying to fully account for the meaning of these quantifiers.
It does seem like, trying to reduce some dogs to like a single specific dog misses the essence of the quantifier.
Right.
This modern idea that noun phrases might signify sets of sets, that's a level of abstraction that, maybe took a while to develop.
Yeah, it is more abstract, but it's a much, more flexible and robust framework. But Aristotle's implicit understanding of quantifiers as relations between sets is, really a vital precursor to our modern conception. Now, moving forward several centuries to, Gottlob Frege, another towering figure in the history of logic whose work has, profound philosophical implications.
Frege.
Yeah.
Often called, the father of modern logic. And I know that he revolutionized the field of predicate logic, introducing the universal quantifier and, the concept of identity and so much more. But our source mentions a twofold contribution to this theory of generalized quantifiers.
Yes. So first, as you mentioned, he invented modern predicate logic, including that crucial variable binding operator. But secondly, and this is probably, even more directly relevant to our discussion, he explicitly formulated that abstract notion of a quantifier as a second-order relation, what he called a second-level concept.
Yeah.
He recognized that the Aristotelian quantifiers were really prime examples of this broader category.
So that's a fascinating connection back to Aristotle. So Frege saw, all, some, no, not all, as fitting within this more general notion of second-level concepts. And his main motivation for this was to move beyond the limitations of that subject-predicate structure, which had, dominated logical thought since Aristotle.
Exactly. He argued that this focus had, really hampered the progress of logic. A key insight for Frege was that these traditional, Aristotelian quantifiers could all be defined in this new framework using the universal quantifier and those standard sentential connectives like negation, implication, and so on. So, for instance, all A are B could be reformulated as for all X, if X is A, then X is B.
That shift, expressing these quantifiers, in this more formal language of predicate logic, that seems like a crucial step towards this generalization we're talking about, right? It's like providing this common language for different forms of quantification.
It was a pivotal move. Now, the main difference, I guess, between Frege's view and this modern understanding of generalized quantifiers, it lies in this explicit concept of an interpretation or a model with a defined universe of discourse. So Frege's logical symbols had fixed absolute meanings. His logical system essentially considered, just a single all-encompassing universe. He didn't really have this idea, which became central with model theory in the 20th century, of a variable universe over which the quantifiers range. That allows us to consider, different possible worlds or, domains of inquiry.
So while Frege identified this abstract notion of a quantifier as this second-order relation, the idea of it operating within this specific, maybe limited universe came later with model theory.
Exactly. So you could say, in a sense, Frege did discover generalized quantifiers, but it remained somewhat in the background. It was really the model theorists in the mid-20th century who explicitly developed and explored this.
Okay, so we've traced the initial seeds with Aristotle and a more explicit formulation with Frege. But how did we get to this modern idea of generalizing the universal and existential quantifiers themselves? What's the key step to seeing them as just two examples among many?
So the key really lies in how modern predicate logic defines the semantics of LNA. It does this by specifying their truth conditions relative to a model. So a model in this context, it consists of a universe, like a non-empty set of individuals, and an interpretation function that assigns meaning to those non-logical symbols, the predicates, the constants, and so on. So a formula is true in a model under a given assignment of values to its free variables if certain conditions hold within that model.
Right.
For instance, for all x, phi of x is true in a model if and only if phi of a is true for every element A in that universe of that model. And there exists an X such that phi of X is true if and only if phi of A is true for at least one element A in the
Right.
universe.
That's standard model theoretic semantics for FO.
Exactly. And now here's where the generalization becomes clear. We can rephrase these truth conditions in terms of properties of sets. So, for any formula phi of X with one free variable X in a model M, it kind of picks out a subset of the universe M, namely, the set of all individuals in M that satisfy phi of X. Let's call this, the extension of phi of X in M. Then we can say, for all X, phi of X is true if and only if this extension is identical to the entire universe M. And there exists an X such that phi of X is true if and only if this extension is non-empty.
So we're shifting our focus from individual elements that satisfy this formula to the set of elements that satisfy it. And then we're looking at properties of that set relative to the universe.
Exactly. And so we can think of eta as denoting those specific properties of these sets. So the property of being the entire universe and the property of having at least one member, respectively. So once we recognize this, it opens up the possibility of considering other properties of sets as defining different kinds of quantifiers. For example, the property of a set containing at least 5 elements, or exactly 3, or an infinite number of elements.
So any property that a subset of this universe can have could potentially define a quantifier. That's huge.
Exactly. And this really leads to the formal definition 1 of a generalized quantifier of type 1. So that means it operates on a single property or set. Semantically, such a quantifier Q is defined as a mapping from any universe M to a collection QM of subsets of M. And then, formula QX phi of X is true in M if and only if the extension of phi of X in M belongs to this collection QM.
So the standard quantifiers fit into this framework really well. For any universe M, AM is just the set containing only the universe M itself. And then ARM is the set of all non-empty subsets of M.
Correct. And we can define a vast array of, other type 1 quantifiers. For instance, AOE5M is the set of all subsets of M that have at least 5 elements. AO3M is the set of subsets with exactly 3. QM is the set of infinite subsets. QRM, or the Riescher quantifier, is the set of subsets A, where the number of elements in A is greater than the number of elements in its complement within M. And then, Kievan M is the set of subsets with an even number of elements.
So we're really exploding these possibilities beyond all and some. And the text mentions that adding these generalized quantifiers to FO really increases its expressive power. And as a philosopher, I immediately think about, what can we actually express now? What kinds of concepts can we formally capture?
Indeed. So there are statements we can express using these extended logics that are, just fundamentally impossible to express within FO. A classic example is the concept of finiteness. So, you can't say in FO that every element under a certain ordering has, only finitely many predecessors. However, we can express this in FOQ, that's FO augmented with the quantifier there exists infinitely many, using a formula like, for all X, it's not the case that QY is less than X, which just says, for every X, it's not the case that there are infinitely many Y that are less than X.
That's a really powerful example of how the expressive power has increased. Q allows us to talk about something that FO just can't. And the Riescher quantifier you mentioned, it allows us to express something about proportions, like exactly half.
Yeah.
That seems like another concept that FO struggles with, especially with infinite sets.
Yes, while you can't directly say in FO that a finite set A contains exactly half the elements of the universe M, especially if M is infinite in FO QR, you can express it. So as not QRX, A of X, and not QRX, not A of X, which basically says that the size of A is not greater than the size of its complement, and the size of the complement is not greater than the size of A, so they must have the same cardinality.
So we're expanding the language's ability to describe properties of collections and their relationships. Now, the text goes on to discuss even further generalization where quantifiers combine multiple variables across multiple formulas. Now, it sounds like we're moving into even more abstract territory. And as a philosopher, I'm really intrigued by what this might allow us to say about relations and structures.
It does lead to a higher level of abstraction, but the underlying principle, remains the same. So a quantifier Q, can have a type denoted as N euro, NK. So K is the number of formulas it applies to, and Ni is the number of variables it binds in that I formula. Our type 1 quantifiers, that was just the case where, K1 and A1.
Right. One variable and one formula focusing on those properties of sets. So what does a quantifier of a more complex type actually operate on, semantically?
So a formula beginning with such a quantifier has the form qx, g, where xe is a sequence of new variables. Semantically, such a q associates each universe M with a k-ary relation qm between relations over M. So the ith argument of this relation is a n-ary relation between individuals in M. That corresponds to, the extension of that ith formula within that model.
So now we're not just dealing with properties of like single sets of individuals, but with relationships between, multiple relations. That could be of different arities. That's a big jump.
Exactly. So the truth condition then becomes cakes cake sia like is true in a model M. If and only if this cake-ray relation QM holds between the extensions of, POCS, interpreted as Nairi relations in M. And that's really the most general definition of a generalized quantifier presented in this article, often referred to as a Lindstrom quantifier.
And those quantifiers that we started, like the Aristotelian ones, like all sum,
Yeah.
they fit into this more general framework, just with the type of one,
Yeah.
because they relate two properties,
Yeah.
the subject and the predicate.
Yes. And for instance, all A or B can be seen as all M, A, B, holding if and only if the set A is a subset of B. Similarly, some A or B is some A, B, if and only if the intersection of A and B is non-empty. Same for no and not all. These are all type 101 because they're establishing a relationship between two subsets of the universe.
And then we have the distinction between, monadic quantifiers, which are of type 1, T1, so essentially they're dealing with sets. And then polyadic quantifiers, which have at least one ni greater than 1 or k greater than 1. So they deal with relations. That seems like, a natural way to classify these.
Precisely. So monadic quantifiers, they operate on properties of, individual elements or sets thereof, whereas polyadic quantifiers can express more complex relationships between, multiple properties or relations. And so the text gives several examples of type 11 quantifiers, such as, at least 5, exactly 3, infinitely many, when the intersection is infinite most, when the size of the intersection of A and B is greater than the size of A minus B, an even number of, and then some logically defined ones like MO, when the cardinality of A is greater than the cardinality of B, and the Hurtig quantifier I, when the cardinality of A is equal to the cardinality of B.
The formal definitions in the text really, they help clarify, what these different quantifiers mean. And those examples of polyadic quantifiers, like W for well ordering, that's type 2, QU, for the existence of an infinite subset whose n tuples satisfy a relation, that's type N, resc most, which extends most to like k tuples, that's type KK, and then RECP for a reciprocal relation within a set, type 1, 2. These really show us the potential of this framework. It seems like we can capture these really complex structures that are beyond simpler formalisms.
They are. They are very powerful. And they're essential for really understanding the semantics of, more complex sentences in natural language, which we'll discuss shortly. Now, a really interesting and philosophically significant aspect of generalized quantifier theory is this principle of topic neutrality.
As a philosopher, that immediately jumps out. The idea that logic at its core should be about the structure of the arguments and not about the specific subject matter, that seems really fundamental.
Exactly. So Mostowski and Lindstrom, they independently incorporated this condition into their definitions of generalized quantifiers. They should not be able to distinguish between isomorphic models. So informally, this means that the truth of a statement should depend only on, structural properties of the universe and how the predicates are interpreted, not on the specific identity of the individuals. So if you have a one-to-one mapping between the elements of two universes that preserves all the relations and constants, then a sentence involving an isomorphism closure quantifier should have the same truth value in both universes.
That makes a lot of sense. We say most A's are B. The truth of that shouldn't change if we just relabel all the A's and B's to C's and D's. As long as that underlying proportional relationship remains the same. Like, the specific nature of the individuals shouldn't matter for the truth of such a general statement.
Exactly. And so formally, if we have two models that are isomorphic, meaning there's that structure-preserving bijection between their universes, then an isom quantifier Q will hold of the relations in the first model, if and only if it holds of the corresponding relations in the second model.
And it seems like most of the logical quantifiers we've discussed so far follow this topic neutrality principle.
Yeah, most of them do. We didn't explicitly mention it in our initial definition only because, as we'll see later, there are some, natural language quantifiers that appear to violate it. But for logical investigations aiming at, generality, isom is almost always assumed. And it has, two significant consequences. So firstly, any sentence in, a language using only isom quantifiers can't distinguish between isomorphic models. So if two models have the same structure, any such sentence is going to have the same truth value. And that aligns with that philosophical intuition that logic should be about form, about structure.
Logic is being about the underlying architecture, not the particular building blocks.
Right. And secondly, for monadic quantifiers, type 1 or 11.1, uh, you know, the isom property has this particularly revealing form. So if we have a model with a universe M and, several subsets, representing the extensions of our predicates, then two such models are isomorphic if the cardinalities, the sizes of the corresponding regions, in that Venn diagram are the same.
Hmm.
So think back to the idea of partitioning the universe based on, whether elements are in A or B or both or neither. What matters for isomorphism, and thus the truth of sentences with, monadic isom quantifiers, are the sizes of these four regions.
So for monadic and isom generalized quantifiers, it all boils down to like the quantities, the sizes of the sets, not the individual elements themselves. That's really interesting.
Exactly. And so, that list of type 11.1 isom quantifiers we looked at least five, most, an even number of, they all illustrate this. Even the Aristotelian ones, can be reformulated in terms of cardinalities. All A or B holds if and only if the number of elements in A that are not in B is 0. Some A or B holds if and only if the number of elements in the intersection is greater than 0, and so on.
So it all comes together. Isomorphism closure for monadic quantifiers essentially boils down to relations between cardinal numbers. So a type 1 isom quantifier, Q of A, it just depends on the cardinality of A and implicitly cardinality of the universe M, if we want to be super precise about, the relative size.
Right. So QM of A is true if and only if a specific relation holds between the size of A and the size of its complement, M minus A. Now, the text introduces another really important concept, relativization.
Relativization. So it sounds like we're taking our quantifiers and making them more context specific. We're restricting their domain of application.
In a sense, yeah. So, like every quantified statement, it implicitly takes place within some overall universe of discourse M, right? So, relativization makes this restriction explicit within the semantics by adding this extra argument to the quantifier that specifies a subset A of M, effectively restricting that quantifier's action to this subset.
So if we have a quantifier Q of type, N, 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 which operates on relations over the universe, then its relativized form, Quail, would have type 1, N, and E. That initial 1 is the restricting set.
Exactly. So the definition is Crel M of A, R, M, M, N, R, holds if and only if Q, the original quantifier, holds within that restricted universe A, applied to those relations R, M, M, R, K, but only considering the elements within A. So we're looking at those relations kind of cut down to A.
And it seems like many of the common quantifiers that we use every day are actually just relativized forms of, maybe more basic logical ones.
Yes. So the text points out all is semantically equivalent to oral, some to aral, at least 5 to oral restricted to a set. And similarly for exactly 3, infinitely many, most, which corresponds to curl, and an even number of, which is covrel. So it seems like relativization is really fundamental to how we understand quantifiers. In natural language, it lets us narrow down the scope.
It's a very elegant idea
Yeah.
that we can get the meaning of these everyday quantifiers by taking these more general logical notions and just restricting the domain they operate over. Now let's move on to expressive power. We talked about this a bit earlier with the limits of FO. So how do we compare different logical systems, especially those with these generalized quantifiers, in terms of like what ideas they can express?
So we compare expressive power by determining whether one logic can say everything that another one can say. So we say that logic LO is at least as expressive as logic LO, written as LO, LO, if every sentence in LO has a, logically equivalent counterpart in LO, meaning they're true in the same models. Two logics, LO and LO, have the same expressive power, so that's LO, L, 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 if LO, LO, L, L. And then, LO is strictly more expressive than LO, 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 but LO is not less than or equal to LO.
So it's basically whether one language can capture all the distinctions in truth and falsity across all possible models that the other language can.
Precisely. And a common way to show that LROs is to demonstrate that, that every generalized quantifier in LO is definable in LO. So a quantifier Q is definable in LO if we can find a sentence in LO whose non-logical symbols are exactly those involved in Q. So this sentence is true in a model if and only if Q holds in that same model.
Like, for example, all arrow is definable in FO using, implication within the universal quantifier. For all x, if A of x, then B of x.
Exactly. And as the text notes, the Resure quantifier, QR, is definable in FO augmented with most, so FO most. And there's a general observation that any generalized quantifier Q is definable in FO extended with its relativized form, FOQRel. And that's kind of intuitive because relativization gives you a way to introduce the specific behavior of Q within, this more familiar framework of FO.
So definability is a key tool for showing, like, positive results about expressive power. But what about showing that a concept or a quantifier can't be captured within a given logic? That seems a lot harder.
It is a lot harder. One powerful technique is to show that the first logic possesses, some fundamental property that the second logic lacks. So FO, for example, has several important model theoretic properties, the Lowenheim property, the Tarski property, compactness, completeness.
And if a logic that has these generalized quantifiers, if it fails to have one of these properties that FO has, then it has to be more expressive, right? Like, it's able to make distinctions that FO can't.
Not necessarily more expressive, like strictly containing FO in terms of what it can say about, purely FO concepts, but it will definitely be able to express things outside of FO. For example, FOQ lacks the compactness property, so we can construct an infinite set of sentences, one saying there are at least n elements for every natural number n, and another, single sentence stating that it's not the case that there are infinitely many elements. So every finite subset of this has a model, like a large enough finite model, but the whole set, it has no model at all. Since FO does have compactness, Q cannot be definable in FO, so FOQ is stronger, at least in some ways.
That's a really clever way to demonstrate that, by finding that fundamental difference in these properties. However, the text notes that this approach often applies to, like, infinite universes, and that there are different techniques used for finite model theory.
Right, so in finite model theory, where we're only looking at models with a finite number of elements, there are, more direct, often more combinatorial techniques to show undefinability. And those very model theoretic properties can actually be used to characterize FO. So Lindstrom's theorem, a really important result, states that any logic that satisfies both compactness and the Lowenheim property must be equivalent in expressive power to FO. And similar characterizations exist based on combinations of completeness, Lowenheim, and Tarski, as long as the logic also satisfies relativization.
Lindstrom's theorem really highlights how special FO is. Okay, so our outline suggests we, briefly touch on some of these remaining sections, focusing on the ones that might be of philosophical interest. So let's start with generalized quantifiers and computation. What are the connections between these two seemingly different fields?
So this section really explores the computational complexity of, determining the truth of quantified statements, particularly, in those finite universes and when we assume isom. So in this context, you can view a generalized quantifier as a set of finite models that, satisfy the quantifier. These models can be encoded as, strings of symbols, like words in a formal language. And the main question then becomes, how hard is it to figure out whether a given word representing a finite model belongs to the set of models defined by the quantifier? And this naturally leads to connections with, automata and formal language theory.
Automata, like finite state machines and Turing machines we see in computer science.
Hmm.
How do those relate to the abstract world of logical quantifiers?
Exactly. So finite automata, those are abstract computational devices that either accept or reject, input strings based on a finite set of states and transitions between them. And so Johann van Bentham showed that the generalized quantifiers that are definable in FO are precisely those that can be recognized by finite automata that are acyclic and permutation closed. More powerful automata, like push-down automata, which have like a memory stack, correspond to quantifiers definable in extensions of FO with, some arithmetic capabilities. And then even more general models, like Turing machines, relate to, broader complexity classes like PTI-Me.
So the logical properties of a quantifier, in terms of, like, can it be defined in certain systems, that has a direct parallel in how computationally complex it is. Like, what kind of computational device is needed to recognize it? That's a pretty amazing connection between logic, which we often think of as abstract, and the concrete world of computing.
It is, and the Immermann-Vardy theorem strengthens that link by establishing that on ordered finite structures, PTI-me is actually equivalent to FO with least fixed point operator, so FO LFP. While the question of whether PTI-me can be characterized by, FO plus some set of generalized quantifiers on unordered structures is still an open problem, results like Hella's theorem show that just adding a finite.